All right, so we're going to take a look at how forces are related to circular motion. So the science of forces and Newton's laws is called dynamics. We look at kinematics, and now we're looking at dynamics. So dynamics refers to forces. And if we take the idea we've learned so far, that in every circular motion, so there's no exception to this. Every time something travels in a circle, it has this thing called the centripetal acceleration. It's accelerating inward toward the middle, because when you're turning or changing direction, you must be accelerating. If we put this together with what we learned back with Newton's laws, and in order to have an acceleration, you need a force, specifically a net force. That means if you're going to have an acceleration that points towards the middle of the circle, you're going to need a net force that points towards the middle of the circle as well. So we can also say that in every circular motion, there is always a net centripetal force. So we're going to be looking for this. When we see objects traveling in circular paths, we're going to be looking for forces that pull inward toward the middle of that circle. And we can actually write this on our equation card as well. It's, rather than just writing F equals ma, which we already have on there, we could write it this way. We can say the net centripetal force is equal to m times v squared over r. So all that I'm doing is I'm substituting. We know that acceleration is v squared over r, so my net force is m v squared over r. Go ahead and put that on your 3x5 card. Anytime anything moves in a circular path, all of the forces have to add up to point towards the middle, and they're going to be equal to mv squared over r. So practically speaking, if we look at the three different variables, if you take a very massive object and try to swing it around in a circle, it takes a lot of force. That makes sense, right? Swinging a bowling ball around is going to be harder than swinging a ping pong ball around. Making a freight train or a boat turn is going to be a lot harder than turning on a bicycle or just turning while you walk. And then speed matters as well. Very fast moving things take a lot of force to turn. Or to turn in a very tight turn with a small radius is going to take a lot of force. They're all showing up in this equation. Now, before we look at some examples, I'm going to draw some pictures here to show you. I want to introduce something a little new. So far, nothing new. There's a really convenient sign convention that we can make. By sign convention, I mean which way we're going to decide to be the positive and the negative direction for our forces. And we're kind of used to making the right be positive and the left be negative, or up positive and down negative. That's not very convenient for circular motion. So in circular motion, if this is the path of the object, we know that the force always points inward. So sometimes that's down, sometimes that's left, sometimes that's at an angle. So rather than having lots of different directions, let's just define the positive direction as the inward direction. So any vector that points inward, like the force will always do, is considered to be in a positive direction. So all of these arrows point in the positive direction. And any arrow that points away from the circle, outward, like these red arrows, would be considered to point in the negative direction. So these are not centripetal forces. They're forces that are pulling you away from the circle. These kind of forces are not going to make things travel in a circular path. Okay. Now before we look at a couple of examples here, let's keep a few things in mind. There are a couple of common misunderstandings people have about the centripetal force. Okay. First of all, what this is not a new force. So if you remember when we learned about forces, we made this big list of forces, and I listed things like tension and friction and the normal force and drag and the buoyant force, all these different forces. This is not just another one to add to the list. It is a net force. It comes from adding up the forces that we already know about. So because it's not a new force, you are to never, ever draw it on a free body diagram. we don't draw net forces on the free body diagram. We just draw the actual forces that are there, and then we add them up to find the net force. So let me give you some examples. This might help a little bit in understanding what we mean by this. Better research. Better. I imagine that probably any force we've learned about so far could potentially be a centripetal force, a force that makes something move around in a circle. So let's think about, well, we haven't looked at a lot of examples so far, but one we've looked at is Barbie's head, right? So Barbie's head is whirling around in a circle. What's the thing pulling Barbie's head inward and making her travel in a circle? Tension, the tightness of the rope, okay? Oops, I'm gonna hit myself in the face. So it could be a tension force. That's one possible centripetal force. I'm gonna draw a picture of this, okay. Woman wearing a mask. Maybe a little bit of hair. Whirling Barbie's head around the end of the rope. I'm pleased with myself. So if I look at the object traveling in a circle, which is the Barbie head, there's a tension force, a tightness of the rope pulling inward. So that means that the tension is equal to mv squared over r. Tension in this case is the net force pulling inward. And so it stands to reason that the faster I swing Barbie's head, the tighter the rope gets stretched. The tension gets more and more. Or if I put a bowling ball on instead of Barbie so it's more massive, the rope's going to have to be stretched a lot tighter. It might even break if I try to do that. So again, this type of motion is unnatural. Remember, forces make things accelerate. What Barbie's head really wants to do is not travel inward. Barbie's head wants to keep going off in a straight line. Straight line motion is natural. This is not a force moving it in this direction. This is inertia. The inertia of Barbie's head makes her want to move tangent to the path. And so this creates a little bit of an illusion. Sometimes when things swing in a circle, to us they feel like they're getting pulled outward. And I can kind of feel that. I feel like Barbie's head's getting pulled outward because I'm holding on to the end of this rope. But in reality, what Barbie's head wants to do is not move outward, but to move in a straight line, tangent to the circle. So when I let go of the string, dare I do this again? Trent's not even looking. It's pretty much a guarantee that he's going to get hit with this Barbie's head. Okay, well, okay. Not that time. Okay. Barbie's head goes flying off in a straight line as soon as the tension is removed. Doesn't travel in a curved path, doesn't move outward. Okay. So that's one example we've looked at. Another example we've looked at is the orbit of the moon. So we're going to look at the moon orbiting the Earth. The moon's traveling, and it's not a perfect circle, but it's actually pretty close to a circle. And just like Barbie's head, as it whizzes around through space at over 1,000 miles per hour, we found, the tendency of the moon is not to travel in a curved path, but to go in a straight line. So the inertia of the moon, its desire, so to speak, is to follow this green path, but a force pulls inward on the moon, specifically here, the force of gravity, as the Earth reaches out and pulls on the moon with its gravity. And the gravitational force here is equal to mv squared over r. So gravity can be a centripetal force and can cause an orbit. Just about any force you can think of can be a centripetal force, even like friction. How could friction be a centripetal force? Well, think about an object that's turning because of friction, like a car or a motorcycle or someone riding a bike. I think I can draw a car best. Try that, say a turning car. This is a little trickier to draw. Let's see, so I'm going to try to draw this two different ways to help us visualize this. I'm going to draw this from like a bird's eye view. So let's say this is the road. We're looking at it from above, Google Earth or something like that. So here's your car. So you're driving down the road. So let's say you're making a right turn. Pretty tight curve here. The tendency of your car is not to move on a curved path, but to go in a straight line. So what your car really wants to do is follow this path. This is where the inertia of the car will take you. And if you don't have friction, if there's no traction with the road, in other words, if you hit some ice or a really slick spot, that's exactly what you're going to do. You're going to go sliding off on the left shoulder of the road. But if your tires grip the road, you will have a friction force pulling you inward towards the center of the circle. And that force is actually a static friction force because your wheels are gripping the road and not slipping or sliding on it. And static friction is equal to mv squared over r. Now, this can cause a problem when it comes to driving around a turn in the car, because as you drive faster and faster, you're going to need more and more friction to make the turn. And we all know that there's a limit to how big static friction can be. So at a certain speed, when you go too fast, you max out static friction and you go into a slide. You kick over into kinetic friction and you slide off the road. I said this is a little challenging to draw, and one thing that you got to recognize here, I mean, in the case of the moon, it's pretty evident the only thing pulling on it's gravity, but there are other forces on the car besides static friction. And it might be helpful to portray the same thing in a side view. You might see diagrams like this sometime. Let's say we're following this car, we're in a car behind it, and here's where my artistic abilities are going to let me down here. So this is the rear of the car, this is the bumper, this is the I Heart Physics bumper sticker right there, the back window of the car, okay? So we're following this car. We'll even have this driver be conscientious and turn their right turn signal on here, so their turn signal's blinking. They're going to make a right-hand turn, okay? So that means that as they travel in a circle, the center of the circle is somewhere over here to the right of the car as they're driving away from us and making the right-hand turn. And but this type of drawing is nice because then I can really show all of the forces on the free body diagram. There's a gravity force, there's a normal force, and there's a static friction force pulling inward toward the inside of the turn, keeping the car from sliding off in a straight line. So this is, again, it comes down to the fact that this centripetal force is a net force. It comes from adding all the forces up. So I have to add all these vectors together. Well, this one and this one cancel each other out, so static friction is the net force. Any questions? So friction can be a centripetal force, tension, gravity can be a centripetal force, and to make life even more complicated, sometimes it's a combination of forces that make this happen. And that tends to happen mostly in vertical circles. And here's where our sign convention is going to be pretty important. So let's think about a car driving on a road like this. So let's say you drive over a hill. That's a pretty good hill here. Your car. So if the road looks like this and you're driving over the top of a hill, the tendency of your car is not to follow that curved path. Really what your car wants to do is keep going in a straight line. This is the path of inertia. And maybe it will if you go fast enough and you lose contact with the road, you might go in a straight line and turn the hill into a jump. Okay? But you are traveling in a circle. You're at least traveling in a portion of a circle. I draw the circle down here. And the center of that circle is right here, below you, as you go over the top of the hill. So when I go to draw the forces that are acting on this car, there's two of them, gravity and the normal force. And usually when we draw the forces acting on a car, like let me draw it over here. If I draw it when the car is on flat road, I've got gravity pulling down, and I've got the normal force acting upward. And I draw this very well. They should be the same size. They basically cancel each other out, right? Same size when I'm on flat road. But when I go over the top of a hill, the force of gravity, well, it's going to be the same. It's just how much the car weighs. But I can't make the normal force be the same as the force of gravity. Then they cancel out. There's no force on the car, and the car just goes in a straight line. Okay? But if the car is going to hug the road, that means the car needs a net force that's inward. So therefore, as you go over the top of the hill, the normal force is smaller than gravity. You're not pressed against the road very hard. You might even feel this when you drive in your car. You kind of lift up in your seat a little bit. Your butt's not pressed very hard on the seat. You feel lighter, because remember, your sensation of weight comes from this force as you go over the top of the hill. So based on my sign convention, remember, inward is positive and outward is negative. That means that gravity, even though it's a downward force, is actually the positive force in this diagram. And the normal force is the negative force, because it points outward. So when I go to use my centripetal force equation, the sum, the net force, is the sum of these two. It's going to be negative normal force plus positive gravity equals mv squared over r. So here I have a combination of two forces together that create my centripetal force as I go over the top of the hill. And the reverse happens when I go through a dip in the road. The car travels through the dip. Now, the center of the circle is above the car. Now the inertia of the car, trying to carry it like this. So the inertia is pressing the car into the road rather than pulling it off the road. When I go to draw the forces on this car, I've got gravity, the weight of the car. But now the normal force has to be more than gravity, because again, I need my forces to add up to point toward the middle of the circle. So I have a very large normal force. And this person is going to feel extra heavy as they go through the bottom of the dip, because they're really pressed hard against their seat so that the net force points inward. In this case, the normal force is the positive force because it points inward, and gravity is the negative force because it points outward away from the circle. So the equation looks very similar, except now it's positive normal force, negative gravity equals mv squared over r when I go through the dip. Are there any questions? Let's do an example. You got a few problems to try for the homework for next time for 5B. We'll see how this equation works in a problem-solving situation. And we'll do a couple simple ones here today. Homework 5B isn't too tough. We'll save some of the harder ones for next time, like some of these more complex ones with the vertical circles. You won't have to do in homework 5B. We'll do some examples of those next time. Let's hit one that you might handle on the homework. Any questions first? Okay. Let's see. Maybe you'll have a problem, I'm sure you'll have a problem on the homework that combines some of the kinematics we've been learning about with dynamics, with forces. Okay. So let's say we've got David, as in David and Goliath. David swings a stone around his head at 75 RPM. I thought we'd throw that in there just because you hear that sometimes. When things are rotating, like the engine of a car, you might talk about the RPMs of your engine. One way to measure how fast something's rotating. In a circle of 1 meter diameter, if the rock's mass is 0.5 kilograms, what is the tension in his sling? So how tight is the sling stretched? How strong does his arm have to be to whirl a rock around at that speed? How much force is involved for this type of circular motion? We'll be using our centripetal force equation to help us figure this out. So we'll make a little sketch. And you can just draw the stone if you like, that's fine. I'm going to draw David just for fun. Give him a sweet little headband here. Rock on the end of the string. If I really had time, I'd draw Dwayne Johnson on the end of the string, but it's only so much time. Wrong rock. All right. So here's the rock swinging around in a circle on the end of the string. What do we know? We know the diameter of the circle, so be careful for that. Sometimes you're given a diameter instead of a radius. So if the diameter is a meter, then the radius is going to be half of that, half of a meter, 0.5 meters. We know the mass of the rock, 0.5 kilograms. And we know the 75 RPMs. So what is 75 RPMs? What does RPM stand for? Does anybody know?
Rotations per minute.
Yeah, rotations or revolutions per minute. So RPMs is actually another way of measuring frequency, the number of times you go around per unit of time. So if I have 75 rotations per minute, I have to do a little unit conversion here to get into my base units, because frequency should be measured in rotations per second. So I need to convert minutes to seconds. 1 minute is made of 60 seconds. So if I cancel out the minute and get minute, and I do 75 over 60, I'll figure out what his frequency is in hertz. So this comes out to be 1.25 hertz. So the rock goes 1 1/4 times around every second. And I need to use this to find the tension in the sling. So, okay, tension. Well, the tension is the tightness in the rope. The tension is the force pulling the rock inward and making it travel in the circular path. So, in order to find a force, I have to use my centripetal force equation. In this case, it's as simple as saying the tension in the rope is my centripetal force and is therefore equal to mv squared over r. So we'll plug the numbers in. The mass of the rock is 0.5 kilograms. The radius of the circle is 0.5 meters. And the only problem I have is I don't know the speed of the rock, but I do know its frequency. So we'll go back to our equation card. We have an equation for that. We've been practicing with this one already. Speed is 2 pi r times the frequency, so I can find the speed of the stone. 2 pi times 0.5 meters times 1.25 hertz. Hertz, don't it, Goliath?
3.93.
You can find the speed. What'd you get?
3.93.
3.93 meters per second. Sounds right. Now we got a number to put in for the speed. So it's really just that number squared because the halves cancel out. So the tension in the rope is going to be 3.9 squared, which is like 15 newtons. And if you remember from way back, a newton is about the weight of an apple. So if you imagine a bag of 15 apples, that's kind of a heavy bag of apples. That's how tight the rope is stretched when you swing this rock around. So it's not like superhuman strength is required to swing a rock around over your head. Okay, but it does take some force. Swing a rock around at that speed. Let's see. Let's do one last one, because you have one in the homework related to friction. So we'll end with this. This will be helpful for that problem. And we'll call it a day. How fast can a car drive around a 100-meter radius curve without sliding if the coefficient of static friction is equal to 0.21. So 100 meters is a pretty gradual turn. The radius is about the size of a football field, but normal coefficients, roughness numbers for cars on the road are probably closer to 0.8 or 0.9. So this would be like a car driving in snowy conditions. How fast could you drive around this curve if the road's pretty slick? So what you'll notice is I'm not telling you anything about the car, how big it is, so apparently that doesn't matter, which is interesting. It doesn't matter whether it's a truck or a car or a motorcycle. All that matters is how much traction the tires have. We should be able to find a speed that the car can drive with. So we draw our picture, which I've already drawn once before. I'm not sure I can draw it any better, but we'll draw the kind of side view of the car again. If our car is making the turn, center of the car, let's say the car is making a right turn, so the center is over here to the right. We have three different forces acting on the car: friction, normal force, and gravity. And friction's providing our centripetal force that's helping us make the turn. And the more force you can have, the more speed you can have. They're directly related to each other. So what we want really is the maximum friction. The most possible friction is going to match up with the highest possible speed we can drive, our maximum speed. So if we apply our equation, we add all three of these forces up, well, these two forces cancel each other out, and it just leaves me with the force of static friction. So the maximum force of static friction is equal to mv squared over r. And it seems like I'm a little bit stuck here because I'm trying to solve for v. I know r, but I don't know the mass of the car. I didn't give you the mass of the car. And I also don't know how much friction there is. But I do know the coefficient. So let's see if we can get something out of that, because friction is, remember our friction equation, the coefficient of friction times the normal force. And that's going to be equal to mv squared over r. I guess that helps a little bit. I could put 0.21 in here, but I don't know the normal force or the mass. Any ideas? How big is the normal force going to be? What's it going to be the same as?
Gravity.
Gravity. And how big is gravity? How would I find that? What's the equation for gravity?
Mass times 5.8.
Yeah, mg. So gravity is mg, then that means the normal force is also mg. Look at what happens. Us times mg equals mv squared over r. The mass cancels out. So if you have a very massive truck, it requires more force to make it turn. There's more mass on the mv squared over r side, but the larger mass also presses it harder against the road, giving it more traction. So it's a canceling effect. Now I can plug the numbers in. 0.21 is my coefficient. G is 9.8. This is equal to v squared over 100 meters. I can find the maximum speed that I can negotiate this turn where friction becomes maxed out. In this case, it comes out to be 14 meters per second. About how many miles per hour is that, Andrews?
28.
Yeah, about 28 miles per hour. That's not very fast for slipping, but remember I told you this is a snowy, icy road. Okay. So you can see why it is that you typically want your friction to be higher than that. And Honestly, mine's maybe a little lower. I was looking at my tires the other day and they weren't looking pretty good. I just barely made it through inspection. I should probably get a change before we get some snow. So that's it. Speaking of, hope we do get some snow tomorrow. We'll see.
Weather just tweeted on it.